I'm going to take a look at the harmonics that are excuse me, produced in stringed instruments. Before I do that, before I start with the harmonics, let's just remind yourselves of what this pattern is called. This is called a standing wave pattern. A standing wave pattern is produced when you vibrate a medium at its natural frequency, at the frequency at which its molecules naturally tend to vibrate at. You will form this, the process is called resonance, and you will form what we call a standing wave. So there's individual waves here, red and blue, traveling through this medium, and what you end up with is a bunch of constructive and destructive interference points, which cause you to actually see this pattern. This is called the standing wave pattern. And the things I look for in the standing wave patterns are footballs. And if we just, oops, missed that a little bit. Oh, missed it, forgot to come back up. So this is 1, 2, 3, 4, 5, 6 footballs in that string that I would refer to. So the number of footballs in a string are going to become important. When you have a string tied down at both ends, it turns out that the only patterns that will resonate in there correspond to this one, 1 football, 2 footballs, this one, 3 footballs, and etc., etc., a whole number of footballs in the string. So now that's what we want to talk about now, is how to get these different waves in a stringed instrument. So the first thing you've got to be able to do is actually draw these things. So I bring this up a little bit. For a string fixed at both ends, for the fundamental, you draw 1 football. For the first overtone, or what we call the second harmonic, oopsie, well, okay, I'll do this and then erase this black football. Keep in mind that the black football here is what we refer to as the fundamental wave. But if I'm going to draw the other harmonics that exist, sorry that my pictures seem to be not corresponding very well with my wording, but just kidding. I'll just stop at 3, I won't do the 4th. Okay, so all 3 of these patterns refer to the pattern of the first harmonic, 1 football in the string. For the second harmonic, you've got to draw 2 footballs in the same place. For the third harmonic, you've got to draw 3 footballs in the same space. So if I get rid of the black in these 2, you see what you have left is the picture for the first harmonic, the second harmonic, and the third harmonic. I didn't draw the 4th harmonic. The 4th harmonic would have 4 footballs. 1, 2, 3, 4. Okay, so that would be the 4th harmonic. Another name for the second harmonic is the first overtone. It's the wave with the next highest frequency or smallest wavelength that will resonate in the string. Third harmonic, or second overtone, is the second harmonic beyond the first that will resonate in the string. So, in order to make a standing wave in a string, if the string has a length L, the very first wave that you can get in there is, well, let me remind you of this first. If this is Kelsey, we're drawing this, or Mr. York, that's how they draw a sine wave. And you allow me to just make it look more like a football, it takes 2 footballs to be an entire wavelength. So if you see only this portion, which is what we see in this diagram, that must be a half a wavelength long. So the wavelength, I hope I didn't go too quick on that, it takes 2 footballs for a full wavelength. So this is the pattern. The second harmonic, is the pattern where lambda, and 2 for second harmonic, is equal to the length of the string. But for the first harmonic, the wavelength is twice as long as the string. Because if the string has a length L, it would take 2 of these footballs to make a full wavelength, and 2 of the footballs are twice as long as the strength of the length of the string, because 1 football is the length of the string for the first harmonic. But with the second harmonic, it takes, that's not a good way to do it, maybe this is the better way to do it. This is the length of the string. So 2 footballs does equal the length of the string. So the second harmonic's wavelength, lambda 2, is L. For the third harmonic, the length of the string is larger than the length of 2 footballs. So for the third harmonic, we say that the wavelength is 2/3 L. And for the fourth harmonic, it's 2/4 L, or what you would probably just call L over 2. And there is a general formula you can use to find that, which is the lambda of the nth harmonic is 2L over N. So for the first harmonic, it's 2L. For the second harmonic, or first overtone, it's just 2L over 2, or L. For the third harmonic, the equation becomes 2L over 3. And for the fourth harmonic, it's 2L over 4, or L over 2. Now notice this interesting relationship. For the first harmonic, the length is 2L. Second harmonic, it's L. That's half as long. The third harmonic is 2L over 3, which is a third of the original. So the wavelengths keep getting divided, get into smaller and smaller pieces. Therefore, the frequencies have to keep getting larger and larger because all of the waves are traveling at the same speed through this medium. And for a stringed instrument, that speed depends on 2 variables, the tension and the linear mass density of the string. So all of these waves, if you can determine the speed of a wave using radical T over L over M over, I messed that up, sorry, M over L. All waves travel at the same speed. All of the way, because this is one string, the medium determines the speed. They're all traveling in the same string, so they're all going to travel at the same speed. Now, before I find frequencies, let me show you this nice little tablet that hopefully you will like. So here's a picture of a guitar. That looks more like a violin. Here's a picture of a violin string. And what they're trying to show you is this white line, what the string looks like when it vibrates at its fundamental frequency. Now, oddly, they chose not to have it end at the actual bridge of the guitar, or violin again, excuse me. But nonetheless, this white, ignore the violin in the background. The white string is trying to show you the 1 football shape. So when you pluck a guitar string, this is the largest wave that will resonate in the string. But there's another wave that will resonate in the string, and it's this diagram right here. This is showing you the wave with the next smallest wavelength, what we call the second harmonic or first overtone, that will also resonate in the string. Now, if you notice this, I think I should be over to lap them. This was the first one. Notice where the ends of the white line are. Again, they don't correspond to where they really would be on the violin, but just notice where the ends of the white line are. The next pattern that has ends of footballs there happened to be this, the second harmonic, with 2 footballs resonating. And then the next pattern that you could get is this, with 3 footballs resonating. Now, they only show half the footballs here, and then, of course, there's a 4th, a 5th, etc. So if I click them all, though, this is what the string is really doing. They're all resonating in there at the same time. So you don't actually see a wonderful picture like when I vibrate the Slinky in class and get 1, 2, or 3 football patterns. This is what the actual string looks like as you vibrate it. But having said, so this is the sum of all the individual waves. It still is just the first, second, third, fourth, and fifth on top of each other. So what you learn how to do, well, I won't go there yet. Let's go back to this picture and come up with what the actual frequencies are. So all of those waves I just showed you are in the same string, so they're traveling at the same speed, but they all had different wavelengths. 2L, twice the length of the string, L, the length of the string, 2/3 of the length of the string, half the length of the string, and then there is 2L over 5, 2L over 6, 2L over 7. All of these harmonics are in that string at the same time. As you get closer to infinity, the amplitude, or the amount that you can actually hear those harmonics, dies away, but they are still there. So what are the frequencies of these sounds? notice that the one thing that's going to be the same no matter what you do is the length of the string. And people have a hard time with this. The length of the string is set. I mean, the manufacturer of the violin determines what the length of that string is going to be. So the wavelengths of the harmonic, first harmonic, and all of its overtones are preset before you start playing it. You can, of course, buy strings with different linear mass densities, and you can put them under different tensions. That will give you different speeds, and therefore, by this formula, you can get different frequencies out of the string for an instrument. But the wavelength of the fundamental frequency of your violin is preset. It's twice the length of the string, and you can't affect that. That's what it's going to be when you play it open. Okay, so if I plug in, instead of lambda, if I plug in V over 2L, that's how you find the frequency of the first harmonic in any stringed instrument. Every single stringed instrument's fundamental frequency will be the speed of the wave, which does depend on tension and linear mass density, so you'll have to calculate that, divided by twice the length of the string. Every single one of those stringed instruments out there that are tied at both ends, you find the wavelength of the frequency of the second harmonic by using the wavelength of the second harmonic, which is just L. So that, V over L, is how you find the frequency of the second harmonic, also called the first overtone, in any stringed instrument. Do notice that V over L is twice the frequency of V over 2L, so F2 is always equal to twice F1 for a stringed instrument. That means the frequency of the first overtone is always twice the frequency of the fundamental, which means that it's always an octave higher for you music geeks. The frequency of the third harmonic is V over lambda 3, which is V over 2L over 3, which is 3V over 2L, which happens to be 3 times the fundamental frequency. So it's 2 octaves higher than the fundamental, but it's not an octave higher than the first overtone. Again, for you music geeks. And do tell me if I said that wrong. Because me, geek, day music, not. Okay, and then the frequency of the fourth harmonic will always be V over lambda 4, which is V over L over 2, which is 2V over L. Did I do that right? Let's hope. Lambda 4, L over 2. Yes, so it's 2V over L. Okay, which is the fourth harmonic is twice the frequency of the second harmonic. So the fourth harmonic is an overtone above the second harmonic. Hopefully kind of interesting to music people. If you're not interested in music, that's fine. Be able to do each of these columns. Be able to draw the fundamental wave. 1 football, 2 football, 3 football, easy. Be able to relate it to L. Some of you will take some practice to do it. Others of you pick that up like nothing. The equation for the speed of the wave, just one more formula this year, right? And then C foo to solve for the wave's frequency, C foo F in terms of V, and never stop at lambda, all right? Don't stop at lambda, always replace lambda somehow in terms of L, and that's how you solve all these. And that's a 15-point part 2 problem on your AP exam and the next test as well. Now, if you followed that, this should be pretty easy. If F1, that might be 400 hertz, whatever it is, if you have some frequency that resonates in the string, the 4 lowest frequencies are always going to be F1, 2F1, 3F1, 4F1. Why is that? Because of the number of footballs that fit into a string. So if you go back to this, you'll find that you always end up with F1, 2F1, 3F1, 4F1, etc. This won't be the case when we get the wind instruments. Not all of them. So subscripts seem to come out a little messed up, but F1, 2F1, 3F1, and 4F1 is what that was supposed to be showing. The first 3 frequencies that resonate after you push lightly in the middle. Okay, what happens when you push lightly in the middle? Watch how quick I can do this. That guy exists. This guy, the first overtone, is in the same string at the same time. So is this one. This is the third harmonic. Ooh. And then, what's left? Black. And then the fourth harmonic. 1, 2, gosh. That's too many. That's going to be 5 footballs. So I'll just stop at 3. So all of these waves are resonating in that string at the same time. The first in red, second in green, blue, and third. If you press lightly in the middle of the string, that means that you're going to kill the red and blue waves because they don't have nodes in the middle. So the red and blue waves die. What that means is you're going to get the first frequency, fundamental, go away. The third goes away. The second is there, so is the fourth, so is the sixth. All right, so every second frequency, if you press lightly in the middle when you play, will continue to sound. Now this is what you call playing an playing harmonics. You hear a mixture of overtones that are similar to, but not quite the same set of frequencies as if you just played the string open. So this would die, but 2, 4, 6, 8, and 10 footballs would live on. And there's similar patterns that you can do with pressing a third of the way down, a quarter of the way down, etc. So here are your 2, 4, and 6 times the original frequency. The first 3 frequencies that resonate after you push lightly a quarter of the way down. Well, this guy, here's a quarter of the way down. All right, so he dies, 3 footballs die. Oof. What lives, though, is the 4 football pattern. Here, let me do it like this. The fourth harmonic will have a node at the end of the first football, which is a quarter of the way down the length of the string. So F1, fundamental dies. 2 F1 dies. 3 F1 dies. 4 F1's there. The next one you'll get is 8 F1 and 12 F1. It's kind of difficult for students to get right, even though it's a relatively simple concept on AP multiple choice. And there they are. Okay, the first 3 frequencies that resonate after you push 3/4 of the way. Well, 3/4 is the same thing as 1/4. You're just pressing at a note on the other end of the string. Ooh, what is this thing? So, given a string of set length and linear mass density under certain tension, the speed is determined by the tension and the linear mass density, mass per unit length. The fundamental frequency wavelength is determined by always fundamental wavelength. It's twice the length of the string. It's determined by the length of the string, not the linear mass density. Now there is, if you take a guitar string, here it is coiled up in a little bag, if you put that on a scale, and you measure its mass and divide that by its length L, that will give you the linear mass density. Okay, so do keep that in mind. By the way, the units of linear mass density are the kilogram per meter. Okay, so you can take a violin string and put it on a scale and measure the mass and then divide it by its length, and that will be its linear mass density that you're using in this equation. But don't try to equate the length of a string to linear mass density unless you happen to know the mass of the entire string. Okay, okie dokie. All right, so if you pluck a string, the fundamental frequency is F1, and the fundamental wavelength is lambda 1, which happens to be 2L. What is the fundamental frequency and wavelength if you press firmly in the middle of the string? Okay, if you press firmly in the middle of the string, this picture comes out of your book. I'm sorry, it's not so good. All right, I said before that, you always get the same set of waves in a string, but if you press firmly in the string, you're basically cutting off that part of it. Now you get fundamental wave that looks like that, and a second harmonic that looks like this. Well, what's the difference? There really isn't much of a difference except the length of the football got shorter by a half. Therefore, all of the wavelengths get shorter by a half, and therefore the fundamental frequency you play here gets twice as large. So you can play the first harmonic this way, based relative to an open string. This frequency will be twice as large as the frequency you get when you just pluck the string open. Why? Because the length of this football has a length. Let's see if I can copy paste it. Of course, who says the 2 guitars in my 2 diagrams are the same size, but let's pretend. All right, so let me copy that. That's the length of the football when you just play it open, but then when you press firmly in the middle, you have a football that's half the length that it was before. I think this guitar got a little bit shorter. So you get a football that's half the length. And lambda is going to be, remember, V over L. So if you get a wave V over uh, frequency is V over lambda. So if the lambda here is half as large as it was before, you're going to get a frequency that's twice as big when you pluck, when you press halfway down firmly. Not playing a harmonic lightly now, you press firmly. Okay. What's going on here? What effect does increasing the tension have on the fundamental wavelength? None, because the fundamental wavelength's always 2L, and you haven't changed L. What about the fundamental frequency? Well, the fundamental frequency, if you tighten the string, is going to go up because of this. Lambda doesn't change. We just said that in part A. But when you increase tension, you make speed go up. That makes your fundamental frequency go up. What effect does increasing the density of the string have on the fundamental wavelength? None, because where am I? I don't know. Give me a second to look at what that is. I transferred file to file. So what happens to the fundamental wavelength when you affect the linear mass density? None. It's still going to be 2L. But what about the fundamental frequency when you use a string of a different density? Again, just like this equation up here, if you increase density, that'll decrease speed. If you increase linear mass density, that'll decrease speed. Increase linear mass density decreases speed. Decrease linear mass density, that increases speed. Any effect on speed has a direct relationship on the frequency. Okay. And then quickly, I'm gonna show you what it looks like when the string's open at one end. You get half a football. And if you get half a football, the wavelength is 4 times L. The speed is still radical T over M over L. So frequency then is going to be V over lambda, which is V over 4L. And I'll just do the second harmonic for you. You have to have the end of a football at one end and an open end at the other. So the next harmonic looks like this. That's the first overtone that you will hear in a string tied down at one end. That wavelength is that of the third harmonic. That wavelength is, well, there's 3/4, okay? There's 3/4 of a wave in L here. So that means lambda is 4, why do I say 4 and write lambda? Is 4L over 3. Oh my golly gosh. The wavelength of the second harmonic, I put that as a 3, I wonder why. I'll show you why. The wavelength of the next overtone you hear is a third of the original wavelength, meaning the frequency of this is going to be V over 4L over 3, which makes it 3V over 4L. Oh my, that's 3 times the fundamental frequency. By definition, that makes this the third harmonic. There is no second harmonic or fourth harmonic that resonate in a string closed at only one end. Now, there were no instruments like this, so don't expect to see a question like this. But this is what the old saw would be, that if you held it down at one end and plucked the other, the saw's overtones will be the first overtone you hear, and I got a mistake in my notes here, the first overtone you hear will actually be the third harmonic. There is no second harmonic or fourth or sixth in a string tied at only one end. And the math shows you why. When you compare lambda to L, you do not end up with a frequency that's twice as great as the original. And a second harmonic has to have a frequency that's twice as large. Now, you don't need this equation, but the lambda of the nth harmonic would be 4L over N for a string fixed at only one end. But if you're going to memorize a formula, memorize it, the other one for the string fixed at both ends. I will say that when we get to a trumpet's going to do something very similar to this. A trumpet or a clarinet or a reed instrument is closed at one end, open at the other. A recorder closed at one end, open at the other. Those types of wind instruments, when we get there next class, do not play even harmonics. They only, because of the way you got to try to squeeze the footballs in, not physics speak, you don't end up with frequencies that are twice as great or 4 times as great or 6 times as great as the fundamental. So wind instruments closed at one end don't play even harmonics.
thought you'd find that cool.